Across the quiet, black ocean of interstellar space, beyond the soft glow of our sun, past the frozen outskirts of our solar system, a signal emerged. Not a radio transmission, not a message in any conventional sense. It was a whisper hidden in the light of a distant star, a chemical fingerprint imprinted onto photons that traveled for 120 light-years before reaching the mirrors of the James Webb Space Telescope. A fingerprint so unusual, so statistically unlikely, that it forced scientists to stop what they were doing and ask a question humanity has whispered for centuries. Did we just detect life? Tonight, we walk through the discovery that shook exoplanetary science, the detection of a 99.7% biosignature on a world named EPX99b. A world that, if the data holds true, may be the first confirmed living planet beyond Earth. This is the breakdown. This is the investigation. This is the mystery. James Webb was performing routine spectroscopy, a standard atmospheric scan of a faint, unremarkable red dwarf star. Its catalog ID was ordinary. Its light output was stable. Its flare activity was low. Nothing about this star stood out. But during a scheduled transit, something passed in front of it, a small rocky planet, EPX99b. As the planet moved across the star, some of the starlight filtered through its atmosphere and carried with it a signature. Webb captured that signature. It expected to see something familiar, carbon dioxide, perhaps some water vapor, maybe a trace of methane, something simple, something explainable. Instead, Webb detected a combination of signals that should not exist together, at least not without something alive maintaining them. The readings were strong water vapor absorption, distinct methane lines, high oxygen concentration, a carbon cycle imbalance pattern Webb had only seen in theoretical models. The instruments flagged it immediately. The first alert had triggered. On Earth, methane and oxygen exist in tension. One destroys the other. In a natural, lifeless environment, they cannot remain together for long, certainly not at the high, stable levels Webb detected. If methane exists in an oxygen-rich atmosphere, it is broken down rapidly, sometimes in a matter of years. The only known process capable of replenishing both gases continuously is biology. Microbial ecosystems, plant respiration, marine metabolic cycles, organic decay patterns. EPX99b showed this exact signature, a balanced but unstable equilibrium that could only be maintained if something on that planet was producing methane faster than oxygen could destroy it. A type of battle, a chemical tug-of-war, one that, on Earth, only life participates in. The probability that geology alone could create this is extremely small enough to trigger deeper investigation. Webb turned its thermal instruments toward the planet and detected something even more startling. An average global temperature of about 22 degrees Celsius. Warm, mild, comfortable, unmistakably Earth-like. Infrared mapping suggested the presence of surface water, not frozen, not vaporized, liquid. Cloud reflectivity hinted at massive oceans, possibly covering 80% of the surface. A world dominated by shallow seas and glistening blue plains. Its atmosphere was thicker than Earth's by roughly 17%, enough to stabilize climate, buffer temperature extremes, and maintain a long-term hydrological cycle. A world with water. A world with warmth. A world with weather. A world that, based purely on physical conditions, should be able to host life for a very long time. Most planets orbiting red dwarfs have stripped atmospheres. Stellar winds carve them away, leaving bare, dead rocks. But something unusual was happening on EPX99b. Webb detected electromagnetic scattering patterns consistent with a planetary magnetosphere, a magnetic shield stronger than Earth's by nearly an order of magnitude. a field powerful enough to block radiation, preserve the atmosphere, and protect any life below from the frequent flares of its star. This raised new questions. How does a small rocky world generate such power? Is it younger than we think? Does it possess a molten supercore? Or has biology itself played a role in regulating its climate over geological time? No clear answers exist yet. But the magnetosphere was undeniable. And it meant one thing. EPX 99b was not a fragile world. It was a survivor. Astrobiology uses a strict framework known as a biosignature lock. For a world to be considered biologically active, it must show all of the following simultaneously: liquid water signatures, atmospheric methane, atmospheric oxygen, a measurable carbon cycle imbalance. Most exoplanets show 1, a few show 2, almost none show 3. EPX 99b showed all 4, clearly, consistently, and in the exact ratios that theoretical life models predict. When the biosignature model processed the data, the result returned 99.7% probability of biological origin. Not intelligent life, not animals, but life. Microbial, ocean-based, planet-wide life. This was the highest confidence rating Webb had ever recorded. Scientists paused. Some celebrated. Others doubted. But all agreed. The planet demanded further investigation. Months later, Webb performed an extended deep scan of EPX 99b as it rotated behind its star. On the night side, a place that should have been dark, cold, and devoid of activity, Webb detected something faint. A glow. Not thermal emission, not volcanic light, not reflected starlight, but a soft, persistent infrared shimmer with a wavelength profile strikingly similar to biophotonic emissions. On Earth, such emissions come from plankton blooms in dark waters, microbial colonies, algae releasing energy in the absence of light. It was as though something in EPX 99b's oceans was glowing gently in the dark, a biological nightlight spread across a planetary sea. It was faint, but real. And it added another piece to an already astonishing puzzle. Then came the discovery that pushed the scientific community past doubt and into cautious excitement. During a high-resolution atmospheric scan, Webb detected a narrow absorption feature that did not match any known Earth molecules. It matched instead a theoretical pigment predicted decades ago, a molecule scientists believed could exist on planets orbiting red dwarfs. They called it chlorophyll F. Like chlorophyll on Earth, it would absorb light for photosynthesis, but not the light we see. It would capture red and infrared radiation, perfectly suited to EPX 99b's dim crimson sun. If this signal truly belonged to a photosynthetic pigment, the implication was staggering. A living world, a photosynthetic biosphere, planet-wide energy cycles powered by alien sunlight. The scientific community took a collective breath. Had we just found alien photosynthesis? Most planets orbiting close to red dwarfs become tidally locked, one side scorched, the other frozen. But EPX 99b didn't behave like that. Atmospheric motion models revealed global heat circulation, winds that moved warmth from the day side to the night side, with elegant, balanced efficiency. This required a thick atmosphere, strong ocean evaporation, constant cloud formation, and stable long-term oceans. This wasn't the climate of a young world. It wasn't chaotic or violent. It was stable, possibly for billions of years. On Earth, life needs two things: water and time. EPX 99b had both, in abundance. Not humans, not animals, nothing with limbs or intelligence, at least not as far as we can tell. The life on EPX 99b, if it exists, is expected to be simple, humble, ocean-dwelling, yet possibly more productive than anything on Earth. Hypotheses include microbial mats coating warm, shallow seas, photosynthetic ocean films stretching across the surface, bioluminescent plankton layers glowing in the dark, floating microbial continents rising and sinking with metabolism, upper atmosphere bioclouds absorbing red dwarf light, reef-like megacolonies forming alien underwater forests. Methane levels suggested high metabolic turnover, meaning whatever lives there is active, abundant, and constantly reshaping its planetary environment. A world alive, not in small pockets, but everywhere. The number is not a guess. It is the output of an analytical model that considers nearly a dozen parameters simultaneously: atmospheric gas ratios, chemical reactions, thermal stability, spectral noise, magnetosphere strength, carbon disequilibrium, possible non-biological explanations, and even photonic scattering patterns. Each parameter supported a biological origin. Each analysis reinforced the last. When the model converged, it did so with unusual confidence. 99.7% probability of biological activity. Not absolute certainty, science rarely deals in absolutes, but enough to move EPX-99b into the category of strongest alien life candidate ever detected. The moment the internal report circulated, research institutions across Earth began analyzing the raw data. University astrophysics teams, exoplanet detection groups, independent spectroscopic analysts. One by one, their conclusions aligned. The atmospheric chemistry cannot be explained by geology alone. Some argued caution, others urged excitement, but all agreed something extraordinary was happening. For the first time, the search for life had a statistically significant target. Even with all its precision, James Webb has limits. It cannot see the surface. It cannot detect organisms directly. It cannot capture images of oceans or clouds. It cannot identify structures or continents. Webb reads chemistry, the invisible fingerprints of a planet's atmosphere. To confirm life, humanity will need a different kind of telescope, something that can see worlds not just as points of light, but as places. In the 2030s, the Habitable Worlds Observatory will launch with capabilities Webb does not possess. It will be able to directly image EPX-99b's oceans, detect surface pigments, observe seasonal patterns, measure ocean glint, identify large-scale biomass distribution, and search for artificial signals should any exist. For the first time, we may capture a photograph of a living alien world, a picture that could redefine human civilization. For thousands of years, the question has persisted: are we alone? EPX-99b does not answer that question fully, not yet, but it shifts the probability. It pushes humanity one step closer to the realization that life may not be a cosmic accident, but a cosmic pattern, a universal phenomenon that emerges wherever the conditions are right. If EPX-99b truly hosts life, then life is not rare, it is inevitable. To conclude, EPX-99b orbits a quiet red dwarf 120 light-years away. It shows water vapor, methane, oxygen, and carbon imbalance. It maintains Earth-like temperatures. It possesses a powerful magnetosphere. It is covered with global ocean. It displays a chlorophyll analog signature. It radiates faint biophotonic light. It meets all 4 criteria of the biosignature lock. The probability of biology is measured at 99.7%. EPX-99b may be the first living world ever discovered beyond Earth, a world whose light has traveled across the void to tell us a simple, quiet truth. Life may not be rare. Life may be everywhere. This is the end of the report, and the beginning of a new chapter in human history.